Good morning. All right. Happy Tuesday, I guess. Daylight savings, but it's the day after the day, so it's not as bad, but ugh. Um, I don't like it. I don't like daylight savings. Um, it doesn't matter which way we're going, I always feel really tired. Anyways. Um, Today we're going to start chapter 6 and kind of sneakily, we're going to skip section 6.1. And the reason for that is because it's inference for a single proportion, which is what we've been working on this whole time. And ideally, we would have had a day to do another example, but unfortunately, we don't have time. And so, what I want is for you to review this on your own. Now it introduces an example and it makes you do a hypothesis test and I think a confidence interval. So that's nice review. And so I'll just scroll through it with you. But this is the same. So the reason I'm skipping it is because it's the same as 5.2 and 5.3. And we spent a good week and a half there, so you can do it. So it's nice to have some more practice, right? Some guided practice. So it introduces a survey, and then talks about the results, and then we want to talk about the proportion of people or of all Americans who have good intuition about experimental design, which is represented by selecting the right option. And then we can build a confidence interval, right? So this is all review, checking the conditions, build a confidence interval. And then this one, so then calculating a sample size. So this is new or not covered, but kind of a fun kind of a fun exercise. But a fun exercise. Whee. Okay. And so I mentioned it briefly. When we have a confidence interval, what we can do is we can say, well, what if I want to force my margin of error to be some number, right? In fact, here, what if I want to force the margin of error to be 0.01, right? Then what sample size would I need? Okay, and so you can work through the example because it's building on the previous example. And you can work backwards and try to solve for it. Now I will bring in from the formula sheet. Oh, I keep bouncing it back and forth here. Where do you think it is? Here. I'm gonna mark it up so that I can bump it to the top. But also here in the sample size calculation, we've got, if I want to solve for the sample size, then I need my critical value Z star. M is the margin of error. So in this case, I'll give it to you. M is 0.01. Okay? And then the slides will talk about what to use for P star, Q star. Okay? And so here, right? What happens? And then just talking about, had to look at it for a second, just talking about the conditions for a confidence interval versus a hypothesis test. They were slightly different, right? Yeah, I keep getting those balloons because I keep going like this. I'm always talking about two things. It seems like. So then hypothesis testing example and thinking about all those things and then a recap, and then here we are. So today I want to do section 6.2, which is the newest or our second type of question. So here, this is the second question type, which is two sample proportions. If you tried to do Lab 8 yesterday, you might have been a little bit confused because we're just introducing it today, but Lab 8 is going to introduce you to, I'm focusing on the confidence interval just because it is kind of off schedule with the class. And so in the lab, we're doing a confidence interval. But today I'll show you how to do both hypothesis test and a confidence interval. So how I want to do this is I want to show you on the formula sheet where we're at, and then we can break it down from there. Okay. So here we finished one sample proportion. That's the type of question that we've talked about so far, right? We did a confidence interval, we did a hypothesis test, and this is the only time where we're going to do a sample size calculation. And like I said, we're not doing it in class, but I'll include it on the assignment. And then how about this? How about I make it a bonus question on test 2? That might be nice. So today, we're moving on to the second page of the formula sheet. Very exciting. And we're going to talk about two sample proportions. Now, it looks overwhelming, but that's only because I want you to have as much information as possible. Okay. So let's talk about what's going on here. Again, the central limit theorem says that, okay, a difference in proportions. So now imagine I have two samples, right? Each with a proportion, and ultimately I want to compare those proportions. Okay. And so we now have two samples of categorical data. And we want to compare the proportions. And we want to compare the proportions. Specifically, what we want to know is if they're different from each other. Okay. Specifically, whether they are different from each other. Whether they are, maybe I'll say the same or different from each other. Yeah. So now what's going to happen is we have information from both samples. Okay, so let's just talk about in the one sample situation, what information did we need? I'll call that sample 1, but eventually, right, I'm going to introduce sample 2, but don't worry, they're all going to have the same information. Right, and so what did we need for a one sample proportion? We needed to find, we needed n, right? We needed the sample size. We needed x, the number of successes. And we needed p hat. Sometimes it was given in the problem, and then we can kind of unravel it to find the number of successes, for example, right? And so this is the information that we needed from the one sample proportion, okay? But now that I have sample 1 and sample 2, right? What am I going to have? I'm going to have N1, N2, right? Using subscripts to denote which group it's coming from. Okay. And often I'll encourage you to use question-specific subscripts. Now, you're not too worried about that because you're being tested online, and so that's not a concern for you. But in general, try to use question-specific subscripts because it'll help you along, right? M and F for male and female, for example. Okay. So then what are we going to have? We're going to have X1 and X2. P hat 1 and P hat 2. So if I want to compare these sample proportions, right? So now I have a sample proportion from group 1 and a sample proportion from group 2. Now, if I want to compare these and want to know if they're different from each other, what can I do? I can look at the difference between them, right? I can subtract one from the other. Okay. And so here, to compare P1 hat to P2 hat, we can consider the difference. Or I shouldn't say can, we consider the difference. Right? How do these two things compare? Oh, I should clean that up. So then I would take P1 hat, oops, minus P2 hat, right? In fact, what we're really trying to learn about is we're trying to learn how P1 compares to P2. Okay? And so now, right, this is for the population difference in proportions. Now, if these two things are the same, if P1 is basically the same as P2, and by basically, I mean, they're allowed to be somewhat different, but I mean, not significantly different. If they're the same, if P1 equals P2, right, then what's P1 minus P2? It would be 0. Which brings me to the null hypothesis that I want to test, right? So this is the null hypothesis, right? But I'm getting a little bit ahead of myself because I did want to talk about the formula sheet. Okay. But I had to introduce the difference in the proportions. So just as before, the central limit theorem applies for a difference in proportions, and they still follow a normal distribution. Why is that exciting? It means that we can use z-scores to calculate probabilities, right, p-values. And it's going to be centered on P1 minus P2, the population difference in proportions. And, this big chunk, if we look at it, it looks very similar to the square root of PQ over N, right? Except now I have information from two places. And so now I have P1 Q1 over N1 plus P2 Q2 over N2. So that's nice. We have to incorporate all that sample information, right? There's no way around it. Now we have so much more information, and so our formulas are going to get a little bit bigger, but just keep track of which sample is which, and then you're good. So if we want to build a confidence interval for the difference in P1 minus P2, right? And so that's the difference between the two groups, right? Our point estimate is from the sample, right? P1 hat minus P2 hat. And then plus minus, so same as before. Z star is even the same as before, so we know how to find that now, right? And from the question, we have P1 hat, which means we have Q1 hat, which is 1 minus P1 hat, over N1 plus P2 hat, Q2 hat over N2. being careful that when you do this calculation, you find these two chunks individually and then add them up and then take the square root. Okay, and so that's going to take a little bit of practice. But notice how, okay, we're actually familiar with all these components, right? It's just that now we have two groups to deal with. Okay, and so here, right, if we move on to the hypothesis test, what are some things that you need from me to be able to do a hypothesis test? Well, you need the null hypothesis and you need the test statistic. Um, and so the null hypothesis we already established was this one here. So the null hypothesis is that P1 minus P2 is equal to 0. The difference between them is not significantly different from 0. Okay, it gets confusing just because we're saying difference in two different contexts, right? That's hard. But if you prefer, you can say that P1 is equal to P2. Okay, but the null hypothesized value here is 0. Okay, and so here, this is the null hypothesized value, which means that this is technically minus 0, right? How far is P1 hat minus P2 hat from 0? Yeah? And then we run into a little bit of a glitch. Now, I don't use this one, so you can ignore the second version if you want. Okay, I'm just going to focus on the first one. They're the same. All that's happened, I guess I shouldn't draw over it if I'm going to talk about it, is this P hat Q hat has been distributed over the ends. I think that's more keystrokes, so I don't like it. So I don't use that one, but some people like it. Okay. Now, what's the deal with P hat? We know we have P1 hat, we know we have P2 hat, and now all of a sudden we have a P hat. Okay, but it also says that, okay, here, where P hat is the pooled proportion estimate. Okay, and so P hat becomes a grouped proportion. Okay, and so there's lots of ways, depending on the information that you have, there are lots of ways to find this. But how I imagine it, and I tried to find the image in a textbook. I've seen it somewhere a long time ago, where it's just this image of a cartoon character pushing all these proportions into a pool, and then all the successes are just successes now, not from group 1 or group 2. It's just all of them together, and all the sample is all together in the pool as well. So that's kind of a fun one. I was hoping to find it, but I couldn't find it. But that's what I think of when I think about the pooled proportion estimate. And so usually where I'm going to be working is here, right? x1 plus x2 over n1 plus n2, right? If you don't have the actual number of successes, then you can calculate it using n1 times p1 hat, right? Kind of work backwards to find x, right? But in general, p hat is the combined number of successes over the combined number of cases. So that's nice. Once we have that p hat, so now there's 3 different p's here, right? And so that's a lot to keep track of. But besides that, we're good. Okay? Now, at this point, I don't expect you to be able to go through and do a confidence interval and conduct a hypothesis test. But why could I expect you to? Let's talk about that. Well, we already know we have all the components for the confidence interval, right? So you can find the confidence interval. Just remember that the interpretation is in terms of the difference in the proportions, right? And for the hypothesis test, let's outline the steps of the hypothesis test. Well, I have my null hypothesis, so state the hypothesis, that's step 1. We're going to check the conditions, and I'm just going to introduce them all right away, just so we have them. They're in the slides later on, but I'll skip through that when we reach those slides because they're separated, and I want you to see them side by side. And step 2 is calculate your Z, right? And so now, once you have a Z, so the Z calculation is different, sure, but once you have a Z, you know how those probabilities behave in step 3 when you have to find the p-value, right? And so now you have your Z score, and you can find probabilities, and then everything is the same, right? Once you have your p-value, if it's small enough, right, smaller than the alpha level, then you can reject H naught and in favor of HA. And then what does that mean in terms of the question, right? So you have all these skills. Now we're just applying it to a slightly different problem. Okay. So before I move on to the example, the conditions for 2 sample proportions are these. So we start with the independence condition. That's the same as before, right? So the the headers of the two parts of the condition stay the same. Okay, and so that's nice. And so now though I have 2 samples, and so I need to check it for each sample. Okay. And so here, let's call it random, right? Because each sample has to be selected randomly. Each sample must be randomly selected. We're going to summarize this as independence within the samples. So this ensures independence within the samples. Yeah. The second condition, now that I have 2 samples, right, one of the things that I'm assuming is that these 2 samples are independent of each other, right? And so we also need independence between the samples. Usually that's just if we've randomly selected each sample, then we can assume that we also have independence between the samples. Okay. And then the third one is optional. It's the n less than 10%, but now we use it for both samples, right? And so the third one is optional. You don't need to remember this one. I feel like I need to include it, especially because it's the first time introducing the conditions. So N1 has to be less than 10% of population 1. And N2 has to be less than 10% of population 2. So we're just broadening the independence condition just a little bit. But really, the only new one here is this one, right? And that each sample has to be randomly selected. The next subsection of the conditions is the normality condition or the sample size condition. Or the sample size. This condition depends on if we're doing a confidence interval or a hypothesis test, right? And so you'd want to read through the rest of the question to figure out what you're going to have to do, and then check all the conditions that are appropriate. And so here, this differs for confidence interval versus a hypothesis test. Whereas the independence condition, they're the same for both the confidence interval, same for the confidence interval and hypothesis test. So those are some go-to conditions that we need to check. Whereas the normality or the sample size condition depends on what we're going to be doing. Yeah? Let's start with the confidence interval. And how about I'll do the hypothesis test and I'll do them side by side. For the confidence interval, I still need at least 10 observed successes and failures in each sample. So at least 10 observed, and I'll highlight that, successes and failures in each sample. And what I'm going to do is I'm going to copy this, and I'm just going to change the observed to expected. So how we're going to check this in the confidence interval, well, the observed is easy, right? Because that's x1 and x2. So if you have those values, then great, right? So it's either x1, which is the same as n1 p1 hat, is greater than or equal to 10. And same thing for the failures, n1 minus x1, which is the same thing as n1 times q1 hat, also has to be greater than or equal to 10. Notice that I'm only talking about sample 1, so now I need to do the same thing for sample 2. What's nice is that this is just tedious. This isn't hard, right? So it's just tedious and not too bad. x2, which is n2 times q2 hat, has to be greater than or equal to 10, and the failures, n1 minus x, or sorry, n2 minus x2, nice try, Emily, n2 minus x2, which is n2 times, oh, I messed it up, I should have had a p hat here, sorry about that. Successes and failures has to be greater than or equal to 10. Notice that this is sample 1, and this is sample 2. Tedious, but not hard, right? And so I have to have at least 10 observed successes and failures in each sample. How am I going to check the condition on this other side for the expected successes? Now, what we're going to do, what's new here, is we're going to use the pooled proportion. Okay, and so here uses the pooled proportion. P hat. Okay, notice the difference in context will tell you if P hat is a pooled proportion, or if you're working in a one sample proportion, then you only have one P hat, so you can just call it P hat, right? But if you have a two sample proportion question, then P hat is the pooled proportion. Okay, and so let's see here. So now if I am looking at the expected number of successes and failures in each sample, then I'm going to be talking about n1 times p hat has to be greater than or equal to 10. N1 times Q hat has to be greater than or equal to 10. Same thing with the second sample. N2 times P hat has to be greater than or equal to 10. And N2 times Q hat has to be greater than or equal to 10. So again, same scenario here. Sample 1 and sample 2. Okay. And I'll say here, where P hat is x1 plus x2 over n1 plus n2. Most simply, right? If you have the number of successes in each group. And of course, Q hat is 1 minus P hat. Okay, nice. So there's a lot, but things have stayed the same from the one sample proportion, right? For a confidence interval, we're going to look at the observed successes. For a hypothesis test, you're looking at the expected successes, right? So that changes a little bit. And now that we have 2 samples, I have to do it for each sample. But besides that, everything has stayed the same. Okay? And I know that's hard to see today because we're just introducing this stuff, but with enough practice, you'll see that everything has stayed the same. It's just I'm introducing another sample. Okay. I think we're ready for an example. Yeah. And so this is how the rest of the question types are going to go, right? I'm going to introduce a new question type, right? I'm going to talk about, well, how do I build a confidence interval? What's my null and alternative hypothesis, right? What is the test statistic? How do I find the p-value, right? If it's something new. In this case, we had a z, so it's nothing new, right? And then the conditions, and then we'll do an example, and then that's it. And then I'll give you an assignment, which I need to post an assignment for chapter 5, the end part of chapter 5. But I'll post that today. Okay, and I'll post one for this stuff as well. All right. Gave you a break over the weekend, I guess. So this example is talking about global warming, and so scientists predict that global warming may have big effects on the polar regions within the next 100 years. One of the possible effects is that the northern ice cap may completely melt. The question is, would this bother you a great deal, some, a little, or not at all if it actually happened? For me, I would say it would bother me a great deal. I don't know. But so here are the results. Now, what they've done is they have asked the general, I think it's a general social survey. So this is all Americans. All Americans, presumably adults, but let's just talk about them. So the entire US. And we're also going to talk about Duke University students. And so the GSS asks the same question below are the distribution of responses from the 2010 GSS, as well as from a group of introductory stats students at Duke University. And so Mina, who's one of the authors of this textbook, she works at Duke University. And so, of course, that's where all her examples are from. And so here, right, this is population 1, and this is population 2. So we have survey information, okay? This is all Americans, GSS, and the subset of Duke University students, and we're interested in whether there's a difference in the proportions. Specifically, and it's not obvious from this blurb, but specifically, we want to compare these proportions, Okay. And so the proportion of Americans who feel that it would bother them a great deal versus the proportion of Duke students who feel that it would bother them a great deal. Okay. And so here, this is the response of interest. We have other responses. What could we do? Instead of saying, oh, a great deal, some, a little, or not at all, we could just zip these up into not a great deal, right? Because those are failures, right? So here, this is a success. And what we can do is we can call this a failure. Maybe I should use a different color. Maybe red. Failures, not a great deal. Oops. For the purposes of this analysis, we're going to talk about, and maybe I'll make this green. Ah, clever. Right, so here, these are successes and these are the failures. I'm going to call this, and hopefully it matches, right? We said this is population 1 and this is population 2, right? Group 1, group 2, sample 1, sample 2. Immediately, what's some information that we have from here, right? Laying out the successes and the failures. Well, let's see here. I have the GSS versus Duke, population 1, population 2. Oh, so laggy. Weird. How's my internet? Should be okay, I think. Weird. That's annoying. Group 1, group 2. Well, what was some information that we needed for each group? I'll do this instead. N, X and P hat. The sample size for the GSS is 680, right? So that means that N1 is 680. N2 then must be 105. Right? I'm forcing group 1 and group 2. The number of successes in group 1 is 454. So X1 is 454 and X2 then must be 69. As proportions, right? P1 hat is 454 over 680, which, let's see here, 454 over 680, I get roughly 0.66. Now, she usually rounds pretty quick here. 668. She might even use less decimal places. I want you to try to keep as many decimal places as you can in your calculations, especially because we're online, and so you'll be working in MOM, the online platform, and so keeping as many decimal places as you can is always good. Notice that you can set this table up very easily in Excel, right? And so then you can manipulate it that way. P2 hat is 105. Oh, sorry. Yikes. 69 over 105, which is roughly 65.7, 0.657, going to 3 decimal places. Okay. So what we want to know is if they're what we want to know is whether there's a difference, a significant difference between 0.668 and 0.657, right? Taking into account the spread. Okay? And so we'll hang on to this information and move through the next slide, which kind of introduces the parameter of interest. Okay. So the population thing that we're interested in is the difference between the proportions of all Duke students and all Americans who would be bothered a great deal by the northern ice cap completely melting. Now, of course, the point estimate would be the difference between these two. And I wish I had scrolled down here because it looks like she's made the Duke students group 1 and the US or the GSS group 2, and that's kind of annoying to me because it's not how they were in the table, but that's okay. So what we've already discussed is that everything's basically staying the same. How do I make a confidence interval? Well, I need the point estimate plus minus some margin of error. We're going to find out what that margin of error is. In fact, we've already seen it on the formula sheet, so you already have it. Okay. To do a hypothesis test, we're going to use a z-score, which is the same. It has the same format as before, right? It has the point estimate minus the null value divided by the standard error of the point estimate. So now we just need to find the appropriate standard error for this point estimate, which is really the only new thing. So we've seen it already. And in general, it's going to be P1 Q1 over N1 plus P2 N2 or Q2 over N2 and then square rooted. Now, we don't have these population proportions. And so we saw for a confidence interval, we end up using P1 hat and P2 hat, right? And then slightly different for the Z, but we're starting with a confidence interval here. So let's check our conditions. Luckily, they're all typed out already, otherwise we'd have to write them all out. But what we need to check is the independence within the groups, right? So I lumped them all as an independence condition, but we first have to check independence within the groups. And so the US group is sampled randomly, and we're assuming that the Duke group represents a random sample as well. We're assuming. That's fine, as long as you say that that's what you're assuming. The sample size for the Duke students, 105, is less than 10% of all Duke students, and 680 is less than 10% of all Americans. And so that optional condition is checked as well. And so now, right, we can assume that these observations are independent of each other. So now we need to move on to the independence between the groups, right? So the sample Duke students and the US residents are independent of each other. Okay, now this is for a confidence interval. So we have to have at least 10 observed successes and 10 observed failures in each of the groups. And I showed you how to find that, but we'll just move on. Okay. Now what I want to do is I'm going to do this because it's got the answers on this slide. So I'm going to add a page here in between and sneak this example in here. Just to be I'll switch from what I defined as population 1 and population 2 earlier, and I'll follow this example, otherwise it'll be too confusing. It doesn't actually matter which one is group 1 and which one is group 2, as long as you're consistent. Yeah, because now she's switched. Rascal. She's switched the order, but also zipped up the failures into just one column. Right? Okay. So now what we have, so this is very similar to what we did earlier together, right? And so here it is just kind of recapped, right? Um, and we want to construct a 95% confidence interval for the difference between the proportions of Duke students and Americans who would be bothered a great deal by the melting of the northern ice cap, P Duke minus P US. All right, so from the formula sheet, let's go back and grab it. We know that, okay, I have two sample proportions and I want to build a confidence interval, right? The question clearly says construct a 95% confidence interval, so that's what we're going to do. Okay. It's so slow. Okay. Sorry, that's really annoying. Did that a long time ago. Okay. Slow internet. Ah. Hello. Okay. I guess I should check in. Is my voice lagging as well? That would be even more annoying. But that I can't tell. Or is it just my screen? I don't know. Okay, that's good. I'll keep blabbing, but I'll keep an eye on the screen here because it's really laggy on my end, at least. I'm assuming because I'm sharing it to myself. All right. So if we let group 1 be Duke and the group 2 be US, right? So what I'm going to say is I'm going to let 1 be Duke and 2 be the US, just to clarify, because that's also opposite of what I did earlier, but that's okay. I'll make a note here that the order doesn't matter as long as you're consistent. You are consistent. Yeah. Yeah. So this is going to be P1 hat, and this is going to be P2 hat. You can make a note of that, but I'm going to just start plugging these in. 0.657 minus 0.668, considering the difference between these two proportions, Z star for a 95% confidence interval, you might remember from the t-table, Z star is 1.960 from the t-table, right? You find that the exact same way that we have been doing it, right? And so that's not different. So I'm going to use that right away. And P1 hat is 0.657 times 1 minus 0.657 divided by N1, which is 105. And, uh-oh, what if can I do this? To make more room for my square root, plus P2 hat, which is 0.668, times Q2 hat, which is 1 minus 0.668, divided by 680 is N2. right? So as long as you're consistent, then it doesn't actually matter which group is which. What's going to change? The only thing that's going to change, depending on which you use as group 1 or group 2, is you're going to get a negative here or a positive here, right? So can play around with that and see what happens, but the interval's not going to change. Okay, now let's see here. I'm going to use this calculator here because I want to show you the calculation steps. Okay, and maybe let's see if I can't have these on the screen together, maybe. Is it going to show? Score. Okay, and this Zoom tab is going to go up there. Okay, so let's see here. Where I'm going to start is I'm going to start with 0.657 times 1 minus 0.657 divided by 105. And I'm going to wrap these up in brackets. 0.657 times bracket 1 minus 0.6, or I'll be proper, 0.657 end bracket, and divided by 105. Yeah. So now what I want to do is I want to add that to 0.668 times 1 minus 0.668. And so here, this answer plus, and I'm going to do the same thing again, 0.668. Oh, I skipped my 0.668 and end bracket. It's bothering me there. Sloppy. Oops. Bump it out. 0.668 divided by 680. Step that out. This is all under the square root, right? So when I hit enter, it gives me the answer. And then what I can do is I can take the square root of that previous answer. So I'm using that answer button a lot. You can, in Desmos, this is the Desmos scientific calculator. I really like it for the line by line entries. You can also name things so that you can say, okay, this is A, this is B, add A and B together. But I just want to show you the steps here. Okay, so now I have that standard error. So let's just jot that down. Now it's really tiny here. So 1.960 times the standard error of 0.052937811035. Ugh. Now I want to make it stop lagging. Okay. I want to multiply that by 1.96 times the answer. And here, maybe I'll say m is equal to this thing. And so now, m, the margin of error, I'll jot that down, is 0.10375811083. Okay. Notice how I've left the point estimate hanging, okay? And so what I'm going to do is I'm going to say P is equal to 0.657 minus 0.668. So this point estimate is negative 0.011. All right. If you reverse that subtraction, it would be positive, right? But the difference between them is the same. So now, in my interval, I want first p minus, hopefully this works. Should have tried it before. P minus m. Phew. And I want p plus m. That's my interval. Okay. And so I'm going to screenshot this and bring it in and scoot this over. Oops, crop it. So I'll just have it there so you can reference it. And we get an interval from roughly, I'm going to use 3 decimal places. It's usually safe to keep as many decimal places as we were given. And so we were given 3 decimal places, and so I returned 3 decimal places. So at 3 decimal places, I'm going from negative 0.115 up to 0.092. Well, I guess that'll be 3. To 3 decimal places. Okay. Now, this is the difference between the 2 proportions. In fact, it's the difference between the 2 population proportions, right? We're 95% confident, right? And so I can't help it. We have to interpret this interval. As soon as you've built an interval, you have to interpret it. So here we go. So we are 95% confident. This is the same blurb as what we were using before, right? We just have to remember that we're talking about the difference in the proportions. So we're 95% confident the interval from negative 0.115 up to positive 0.093 captures what? Captures the thing we were asked to build a confidence interval for. And so here captures the difference between the proportions of Duke students and Americans who would be bothered a great deal by the melting of the northern ice cap. Because I don't want to write that all out. Captures the difference between the proportions of Duke students and Americans who would be bothered a great deal by the melting of the northern ice cap. You don't need to include that. Okay. Nice. So the key is that it's the difference between these 2 groups. If the difference goes from a negative to a positive, 0 is one of the options, right? And so we can use this confidence interval to say, it doesn't look like I'm 95% confident that there's no significant difference between these 2 groups, right? Because 0 is an option inside that interval. And so we can use that to do an informal hypothesis test. Okay, and so I've included that on the lab this week as well, just to show you that you can use a confidence interval to do a hypothesis test. And so, all right, in the interest of time, right, we found, did I find those same values? Oh, it's because I didn't use rounded values. In fact, I could have used the exact proportions here. I didn't, I used rounded values. So my values are a little wonky, but that's okay. So here's the same problem that we worked through, but I want to go through a hypothesis testing question. Okay. So here, which of the following is the correct set of hypotheses for testing if the proportion of all Duke students who would be bothered a great deal by the melting of the northern ice cap differs from the proportion of all Americans who do? Okay. And so there are a couple of things to keep in mind here when we're choosing in a multiple choice scenario. Let's eliminate all the wrong answers, right? So first off, what I want to find is, well, I want to talk about the population, right? So talking about the sample doesn't do anything for me. So immediately B is out. Okay. I want to know if there's a difference. Where am I going to see that? I'm going to see that in the alternative hypothesis, right? And so here, this means I have a not equal to in my alternative hypothesis. So I'm going to skim my alternative here. I have a not equal to, so those are fine still. But here, I'll circle the things that are wrong. Right? So what we're going to find is that both of these are correct. And we've already seen it, right? So here, I'm going to encourage you to think of it this way. Although for me personally, it's easier to think about it this way, right? But it's more clear that this is the null value, right? And so in our hypothesis test, it's helpful to think of it this way. But C and A are both correct. Why? Because let's start in A. If P Duke is equal to PUS, then P Duke minus PUS must be 0, right? You can just move the PUS over, subtract it to the other side, then you're left with a 0 on the right, right? Same thing here. You could add PUS to both sides, and you could have P Duke equals PUS, right? Or just kind of thinking about it, if they're the same, then the difference must be 0, right? So that's a good start. So we've already talked about the conditions. And so here, I'm going to skip to the pooled estimate of a proportion, and we're going to talk about the pooled successes, right, over the pooled sample sizes. And we want to calculate the estimated pooled proportion of Duke students and Americans who would be bothered a great deal, blah, blah, blah. So we have X1, X2. So what we're going to do is we're going to take those successes, the total successes over the total sample size, and we're going to get this new pooled proportion. Notice, right? It makes sense that if I'm pooling these two, what's going to happen? My pooled proportion should be somewhere in that realm, right? Somewhere in that same realm, right? It's going to be overpowered towards the bigger sample, but that's okay, right? And so it's going to be, so notice here, so the pooled proportion, this is just a way of checking to make sure that you did it right. The pooled proportion should be between P1 hat and P2 hat. So now we have these three different proportions, right? I have P1 hat, I have P2 hat, and I have P hat, the pooled proportion. Now the pooled proportion is what I'm going to use to check my conditions. Now I think, do they do it? No. I don't think I have time to check the conditions, so I encourage you to try it on your own, and you'd use the the pooled proportion for the expected successes and failures. Uh-oh. Add a page. I want to do these data suggest that the proportion of all Duke students who would be bothered a great deal by the melting of the northern ice cap differs from the proportion of all Americans who do. And so what I want to do is I want to go through the step-by-steps and work through this problem. It is summarized on the next slide, but of course I want you to see all the steps thoroughly. So step 1 is state the hypotheses. Now, the null hypothesis that I'm going to use is P1 minus P2 is equal to 0. In fact, I'm going to use P Duke minus PUS is equal to 0. I'm going to let 1 be Duke and 2 be the US. In my hypotheses, it's always nice because I'm going to have to talk about these proportions later. And so then I'm going to use these question-specific subscripts. But in my calculations, it gets way too messy to write Duke and US all the time. So I'm just going to use 1 and 2. But in my hypotheses, I want to know how they compare. P Duke minus PUS is not equal to 0, right? I want to know if it differs. Oops. This makes the not equal to. I want to know if there's a difference between the two. Yeah. Good. So now the conditions that we're going to check, the independence conditions we've already checked. I said I wasn't going to, but checked earlier for the confidence interval. And so I'm going to focus on the normality condition. I want N1 times P hat, which is 105 times 0.666. Times 0.666 is 69.93, which is greater than or equal to 10. That's good. N1 times Q hat is 105 times 1 minus 0.66. Or let's just do this, 105 minus 69.93. Could do that. If it's not a success, it must be a failure. Good. So sample 1 is all checked. Sample 2, sample size of 680 times 0.666. 452.88 is greater than 10, and N2 times Q hat is 680 minus 452.88, which is 227.12, which is greater than 10. Whew. Step 2. Do the test. It's really calculate the test statistic, but I find that that's really boring to say. So I call it do the test. Doing the test, Z is P1 hat minus P2 hat, right? Your point estimate, and this is on your formula sheet. And so you can use that or just follow along here. minus the hypothesized value. Now notice here, H naught says that P1 minus P2 is equal to 0. So then this is equal to 0. So we're seeing how far is the sample difference in proportions from 0. So usually, and on the formula sheet, I don't even include this because it'll always be 0. Okay. Divided by the square root of P hat Q hat times 1 over N1 plus 1 over N2. That's square root. Okay. So, all right. Let's see here. So I'm going to use, I am going to use Desmos again, clear all. Okay. And I have P1 hat. So P, or can I use the point estimate is equal to P1 hat, which is 0.657 minus 0.668. Huh? Oh, it doesn't like the point. How about I use E for the estimate? Oh, it doesn't like E because it's a special number. Okay. P. The standard error is going to be, now I'm going to do the 0.666 times 1 minus 0.666. Okay. And I'm going to call this A just for simplicity. There's no reason to use A, but I'll use B is equal to this. What am I going to do here, right? I want to make sure that I multiply P hat Q hat, and then I want to find 1 over N1 plus 1 over N2 just on its own. So I'm going to call that B. And so I've got 1 over 105, step it out, plus 1 divided by 680. Okay. So now I want the square root of A times B. Okay. Let's see here. That's my standard error. So I'll call this S is equal to this. And now I want P minus 0 divided by S. P minus 0 I'm not going to do, divided by S. And I get this, oops, saved photos, this Z. Think about whether you're surprised by this Z or not. Not really, right? Because from the confidence interval, we said that it can be 0, right? And so we're expecting this difference in proportions to be close to 0. So here we get Z is negative 0.2224, let's say. Okay. So now in step 3, and let me just see here. Page, good. Step 3, find the p-value. Now that I have a Z, I use the same methods as I used before, right? I'm going to say the absolute value of Z equal to negative 0.2224 is somewhere between values on the t-table, right? And so let's see here. on the table, which is probably in here. There, oops. Then I find, copy. Oops. Then I find, paste image. The absolute value makes it positive, right? So then I try to place it on this number line. And where does it go? It goes here. I don't even get to start. What's it cozying up against? It's cozying between 0 and 0.674. And so here it's somewhere between 0 and 0.674. Which means that the p-value, right? And let's go back and remind ourselves whether we have a one-sided or a two-sided test. It's from the alternative. I want to know if they're not equal to each other, right? If it's not equal to 0. And so I have a two-sided test. So the two-sided p-value is somewhere between, now here, this is at 0.5 and this is 1. And we've talked about why that is. And so I have a two-sided p-value that's somewhere between 0.50 and 1. Huh. Okay, so now for our conclusion, step 4 is the conclusion. And I want to bring this little guy in. Some call him, this little guy, Snoop, to help us remember. Oops. It's a little risque, but it does help me, it's helpful in remembering what your conclusion is. Good old paste with my mere moments left. Come on. Well, it won't let me do anything now. Come on. There he is. If the p is low, then the null hypothesis must go. Okay? So if the p-value is small enough, you have enough evidence to reject H naught, right? And so what I want you to do is I want you to write the conclusion, making sure that you cover each of those 3 steps, right? The 3 parts of the conclusion, and then that's where we'll pick up as review next day. Okay, if you have any questions, let me know. Otherwise, I'll see you on Thursday. Stop this.